Something from another star system just left our solar system forever. And the last thing James Webb did before it crossed beyond reach was look at its chemistry. What came back from that analysis was published in the journal Nature 2 months ago, and the lead scientist who ran the study described what he found in a single sentence that is still echoing through the planetary science community. This was a unique opportunity to study an ancient object from the distant galaxy, probably predating our sun and solar system. On the one hand, we get direct insight into that distant time and place, and on the other, we learn something about how unusual our own solar system may be. That sentence, from Martin Cordner, astrochemist at NASA's Goddard Space Flight Center, is the one to carry into everything that follows. Because what the Webb data revealed about 3I Atlas is not just that it is unusual, it is that it is a sample, the only directly measurable sample, of a chemical environment that existed in the Milky Way before our sun was born. And we just had it in our solar system for 7 months. And we caught it, just barely. 3I Atlas was first spotted on July 1st, 2025, by the Atlas Survey Telescope network in Chile. It had actually been moving through the outer solar system since at least May 2025, captured in pre-cover images that were found after the discovery. Its orbit was computed within hours. The eccentricity came back at 614. Nothing on a gravitationally bound orbit around the sun has an eccentricity above 1. An eccentricity of 6.14 is not slightly unbound. It is so far beyond solar escape velocity that the object could only have come from interstellar space. The fast-moving comet, which originated outside our solar system around a different star, was discovered as a tiny speck moving across the vastness of space. And when discovered, it was about 410 million miles from the Sun, within the orbit of Jupiter. It is only the third confirmed interstellar object ever detected. The first was 1I Oumuamua in 2017. The second was 2I Borisov in 2019. 3 in 8 years. Scientists estimate an interstellar object may pass through our solar system roughly once per year, but detecting them requires the right telescope at the right time, and most of them pass through unnoticed. Humans only recently developed technologies capable of spotting interstellar objects passing through our solar system. With the advent of ever more powerful telescopes, these discoveries will become much more common. We are at the very beginning of being able to see what the galaxy sends through our neighborhood. 3I Atlas is the third one we caught. It will not be the last. Within days of discovery, NASA pointed Webb's near-infrared spectrograph at the comet on August 6, 2025. The results were immediate and striking. The latest observations confirmed that 3I Atlas was producing a large carbon dioxide-rich cloud of material around the object, commonly referred to as its coma. The unusual carbon dioxide abundance was accompanied by traces of water, carbon monoxide, sulfur compounds, water ice, and an abundance of dust. The carbon dioxide to water ratio in the outgassing was the highest ever measured in any comet, not just among interstellar comets, among all comets ever studied. Webb's observations confirmed that 3I Atlas was releasing far more carbon dioxide relative to water when compared to typical solar system comets. Most solar system comets show roughly equal parts of carbon dioxide and water, or even less carbon dioxide. 3I Atlas was generating carbon dioxide at more than 20 times the rate it was generating water vapor, an entirely different chemical balance than anything formed in our solar system. Then, the comet passed closest to the Sun on October 29, 2025, swung around at a distance of about 1.35 astronomical units, roughly the orbital distance of Mars, and began heading back out. Its ancient ice, which had been sitting at temperatures near absolute zero for billions of years, had now been heated by the Sun for the first time. The volatile compounds buried beneath its surface layers were venting into space, and that post-perihelion outgassing window, brief and closing fast, was the best opportunity Webb would ever have to read the full chemical inventory of what was inside this object. Webb's MIRI instrument, the mid-infrared instrument, observed 3I Atlas on December 15th, 16th, and 27th, 2025. The first observing sessions were conducted when the comet was about 205 million miles from the Sun. The second when it was about 236 million miles out and cooling fast. For the first time on an interstellar visitor, Webb directly detected gas. Methane is highly volatile, meaning it sublimates from solid ice into a gas very easily. Its delayed appearance in 3I Atlas suggests it was buried below the comet's top surface layer and protected from sublimation, until heat from the comet's close pass to the Sun reached deeper parts of the icy subsurface. The methane detection is a first in the history of interstellar object observation. Never before had methane been directly measured on a comet from outside our solar system, and the amount was extraordinary. The methane-to-water ratio was roughly 11 times higher than any previously measured solar system object, 11 times higher than anything we have ever seen in a comet formed around our own sun. Not slightly elevated, not statistically interesting, 11 times higher. Whatever environment 3I Atlas formed in was saturated with methane ice in proportions that have no parallel in the chemistry of our solar system. And then came the NIR spec analysis, the near-infrared spectrograph data from December 2025, processed and published in Nature on June 22, 2026. This is the paper that stopped researchers. Astronomers used NIR spec to discover surprising details of 3I Atlas's chemical makeup, with ratios of heavy carbon and heavy hydrogen never seen among comets in our solar system. Two specific measurements: carbon isotopes and hydrogen isotopes. Carbon exists in two stable forms. Carbon-12, the common variety, has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. It is slightly heavier. Carbon-13 enrichment happens through specific chemical reactions that occur in the warm, dense environments around young stars, the kind of environment our own solar system passed through during its formation. NIR spec data revealed only small amounts of carbon-13, as opposed to its lighter counterpart carbon-12. Since carbon-13 enrichment is known to occur in warmer, denser stellar environments, its absence in 3I Atlas suggests the comet did not form anywhere near such conditions. Then hydrogen. The same logic, but carried further. But deuterium is heavy hydrogen, a hydrogen atom with an extra neutron in its nucleus. The ratio of deuterium to ordinary hydrogen in a body of ice encodes the temperature conditions during that ice's formation. Cold environments far from stars produce high deuterium to hydrogen ratios. Warm environments, proximity to a star over a long period, process that ratio down, converting deuterium-enriched water into the ordinary water we find in our solar system's comets and in Earth's oceans. They found 30 times more heavy water in the Interstellar comet compared to the typical solar system comet, and more than 40 times the heavy water found in Earth's oceans. 30 times. The ice inside 3I Atlas has a deuterium enrichment 30 times higher than what the warmth of our solar system has produced in comets over 4.6 billion years of processing. That enrichment was not created by 3I Atlas's brief pass near our sun. It was baked in at formation and preserved, frozen, through the entire journey across the galaxy. The only way to preserve deuterium enrichment at this level for this long is to never get close to a star, to drift through interstellar space in the cold and the dark for billions of years, with the ice chemistry locked in place since the moment the object formed. Working backward from those isotope measurements, researchers estimate that 3I Atlas may have formed 10 to 12 billion years ago. That is nearly 3 times the age of our solar system. At the upper end of that range, the object is less than 2 billion years younger than the universe itself. The stars it formed around, in whatever distant planetary system produced it, are almost certainly dead. The planetary system itself, if it had one, has had the entirety of Earth's existence plus another 5 billion years to evolve and change. Whatever sent 3I Atlas into the interstellar void happened before the sun existed, before any planet in our solar system existed, before the chemical processes that eventually produced life on Earth had begun. Stephanie Millam of NASA Goddard, co-author of the study, put the implication directly. For us as scientists, finding these rare isotopes is fascinating, but the bigger picture here is looking at the possibilities of prebiotic chemistry elsewhere in the galaxy. So far, we know of only one place in the vast cosmos where chemical ingredients led to life, our solar system, our Earth. Analysis of these interstellar objects is a major step towards learning how common or uncommon the conditions for the evolution of life are in the universe. That framing is the one that matters beyond the chemistry. 3I Atlas is not just an old comet. It is a sample of a formation. We cannot visit from a star system we cannot identify, from an era of galactic history that produced stars and planetary systems under conditions we have never directly measured. The deuterium ratio, the carbon isotope ratio, the methane and carbon dioxide proportions taken together, these constitute a chemical fingerprint of a planetary formation environment that was categorically different from the one that produced our sun, our planets, and ultimately us. And 3I Atlas carried that fingerprint across the galaxy, frozen, and then vented it into space right where we could catch it. The fleet of instruments that studied this comet during its 7 months in our solar system was unlike anything ever assembled for a single target. Hubble, Webb, Spherex, Maven, TESS, Parker, Solar Probe, Europa Clipper. The Lucy spacecraft spotted it from 240 million miles away en route to Jupiter. Mars, orbiters caught images as it swept past the red planet. Few, if any, comets have ever been observed by as many spacecraft as 3I Atlas. Combining data from these different missions delivers powerful new insight that no single mission could provide. And all of that data is now in NASA's public archive, available to researchers who will spend years extracting results from it. A comprehensive CTI search found 0 radio technosignatures. 3I Atlas is not an alien spacecraft. The scientific community examined that question, and the data answered it cleanly. What it is, instead, is something equally extraordinary in a completely different direction. The oldest object ever studied in our solar system, a chemical archive from the early Milky Way, preserved by cold and time, delivered by gravity to a point in space where the right instruments existed to read what was inside it. Martin Cordner described what that means in terms that carry the full weight of what was just accomplished. Interstellar comets give us the opportunity to reach out across space and time through the galaxy to study close up the planet-forming regions of other star systems. Close up. That phrase is doing all the work. The planet-forming regions of other star systems are billions of light years away and completely unreachable by any instrument we have ever built or could build in any foreseeable future. 3I Atlas brought a piece of one of those regions here, and Webb read it in December 2025, and the paper appeared in Nature in June 2026. And the comet is now gone, heading back into the interstellar medium from which it came, carrying whatever is left of it after 7 months of solar heating. It will not come back. No signal will follow it. We have what we collected. And what we collected is the chemical fingerprint of the early galaxy. That is what the Webb data showed. That is what the truth is. And it is not worse than expected. It is bigger than expected. We reached back 10 billion years into the history of the Milky Way without leaving our solar system. The universe sent us the sample. We were finally ready to read it. And there is one number worth carrying out of this story above all the others. Scientists estimate an interstellar object may pass through our solar system about once per year. We detected 3 in 8 years because we only recently built the instruments capable of seeing them. The Vera Rubin Observatory, which officially began its 10-year legacy survey of space and time on June 30th, 2026, is expected to detect interstellar objects at a dramatically higher rate than anything that came before it. The next one will not catch us unprepared. Webb will be ready. Hubble will be ready. Every instrument that scrambled for 3I Atlas knows exactly what to do now, and whatever the next interstellar visitor carries inside its ice, whatever corner of the galaxy and whatever era of galactic history it came from, we will be pointing the right instruments at it before it gets away. 3I Atlas passed through. It left. And what it left behind, frozen in a data archive and published in Nature, is the oldest sample of the galaxy any human instrument has ever directly measured.